Hey, welcome to the reflection video for FEDD 2019. We're the Geiger Gang, and our project was the nuclear power probe. My name's Barton.
My name is Seth McElfresh.
And I'm Peete.
To start, the engineering design process was integral to the way we approached our project. We went through several cycles and subcycles as we perfected our design for the final test according to these principles. So the first step of the process is to ask, in which we go over our problem. So using a measurement related to the brightness of the Cherenkov radiation coming off of the cores of the reactor here on campus and 3 known reactor power levels that were given to us, we are supposed to estimate the power output of a 4th unknown level. Our project had many constraints, but the most important of these was that it had to be waterproof, constructed of an inert material so that it did not react within the pool, and it had to be under $40. Considering our constraints, we came to 3 main contentions. First of all, we had to decide whether to use a photoresistor or photodiode to pick up the light, which each one had their pros and cons. We also had to figure out how to seal our probe and prevent water from getting in when it was submerged. And finally, because we lacked the proper tools, we had to figure out how to cut our acrylic window and allow light to flood the inside of the probe.
The next step of the design process is the planning stage. The most important part of this step for us was gathering materials. Our team member Seth thankfully had a car on campus, which allowed us to buy most of our parts at Home Depot. This cut down on costs and made it far more convenient to get what we needed. We also used the Daniels supply closet for several of our more expensive parts, namely the PVC piping itself and the multimeter that we used to take our measurements. Finally, for our last-minute requirements, we were able to order on Amazon and take advantage of free Student Prime. The 4th step of the design process was the creation stage. The act of construction was rather simple. We simply sealed the pipe using PVC cement. PVC cement literally melts the parts together, essentially creating one contiguous piece of PVC. For the window, we cut it at the ECE makerspace on Centennial. This only required a short training session, and the professor there was more than willing to help us work the tools available. I would recommend this to anybody going into engineering of any kind, as a suite of machines and parts available was very helpful. For the inside electronics, we twisted the contacts of the photoresistor together, with the wire running up the probe, to prevent it from coming undone. We also twisted the wire to prevent it from tangling, as shown to the right. The next step of the creation stage was testing. We ended up using our multimeter to test each photoresistor individually to ensure that they each functioned properly. We ordered a bulk amount of resistors on Amazon, which made sure that we had many functional parts, as there is a small chance of defect in any one part. We also tested the waterproofing of the probe in the University Tower swimming pool. We're very glad that we did this, and we'll get into more detail about that in the next section. The next step of the design process was improvement. We faced several design challenges throughout this stage. First of all, as we discovered the first time we tested in the pool, our waterproofing was faulty. The entire probe ended up flooding with water. We solved this problem by adding more PVC cement and using silicone caulk as extra insurance. Secondly, as we were attempting to move the probe in its complete 15-foot length from my room on the 4th floor, we could not get it down the stairs. Instead, we tried lowering it over the balcony and passing it down to another team member on the floor below. The stress that this put on the pipe ended up snapping one of the joints completely. To fix this, we reinforced that joint with even more PVC cement, and we decided to leave the pipe in a 10-foot and a 5-foot segment, which could be screwed into each other. This made transportation much safer and far quicker. Here are the results from our test day. From the results shown here, which we required at known power levels of 100, 300, and 500 kilowatts, we were able to construct a linear model. From this linear model, we plugged in the 4th reading to find our estimated unknown power level of 600 kilowatts. On the day of FEDD, we learned that the actual unknown power level was 650 kilowatts. This means that our reading had a percent error of 7.69%. Given that we were limited by a very restrictive budget and a rather short time frame, this is pretty good. Shown here is the graph we constructed from our data. As you can see, the readings we acquired fit almost perfectly to a linear regression.
We are happy to report that we were awarded 3rd place. On testing day, a judge was surprised with the depth that we put into explaining each one of the constraints to our project and how our probe fit within them. Several people asked how our probe worked. We would explain that Cherenkov radiation is when particles move faster than the speed of light. This causes a blue glow. The photoresistors in our probe measure the intensity of the light to determine the output of the nuclear reactor. If we had the opportunity to do the project over, what would we change? First of all, we would shorten our probe from 15 to 10 feet. This would both save money on materials and make transportation much simpler. The probe only needed to go into the cooling pool a few feet, so a 10-foot long probe would have been plenty. Secondly, we would have bought a plexiglass window that was pre-cut to the size that we needed, rather than attempt to cut it ourselves. The window that we cut ended up being a little crude, and a pre-cut one would have been much neater. Finally, we would have allocated more of our budget to sourcing a higher quality photoresistor. Additionally, rather than buying a pack of 20 cheaper ones, we could have searched for a few more accurate photoresistors that cost a little bit more. This would have likely reduced our overall percent error. We have a few words of advice for next year's FEDD students. First of all,
Start early. Make sure you have everything you need before you start construction.
make sure to test your probe's waterproofing before the day of the final test.
Don't inhale PVC cement fumes or get the cement on your skin.